Welcome back to the Deep Dive, where we take your stack of complex sources and turn them into crystal clear knowledge. We've all gotten used to AI systems completely blowing our minds. Large language models, vision systems, they're just amazing at pattern recognition, natural language processing. But here's the thing, the fundamental constraint that the research community is really grappling with now. These systems, despite all their capabilities, are locked into architectural decisions made before they ever see the light of day.
That's it. That is the hard limit of contemporary AI. You can fine-tune the parameters, sure, the connections between the fixed nodes, but the architecture itself, the actual shape of the network, it's static.
So it's like a master mechanic who's amazing but can only work in a garage where the walls and the layout are poured concrete.
Exactly. The mechanic can get new tools but can never add a new wing or, tear down a wall to become more efficient.
And that very constraint is the motivation behind the sources we're digging into today, specifically this theoretical framework from a 2025 paper by Caulfield and his team. Our mission is to unpack their vision for something entirely different. Liquid Adaptive AI, or LAI.
And that word liquid is really the key here. We need to get what it implies. It means continuous malleability.
Not just learning, but changing shape.
Precisely. It's the idea of a system that can continuously reshape its own fundamental structure, its own brain wiring, to fit the contours of any problem. This is a huge shift, moving from these sort of episodic training cycles toward persistent, autonomous development, a bit like what we see in biological intelligence.
So we're not just talking about a smarter algorithm, we're talking about an AI that can literally redesign its own topology on the fly. We're going to dive into the three big theoretical mechanisms that make this happen, but first, I think we need to really appreciate just how rigid today's AI actually is.
That's where the paper starts, and it's critical. Traditional AI, it's all about a fixed architecture, a static knowledge base, these discrete training cycles, and this is the big one, human-directed updates.
And LAI is the exact opposite.
The exact opposite. Self-evolving architecture, a dynamic knowledge graph, continuous learning, and autonomous evolution.
Okay, that's great on a slide, but what are the specific functional problems that current AI runs into because it's so static? The authors point to 5 big constraints. Let's really hammer these home for everyone listening.
Right, so the first one is what they call parameter rigidity. You mentioned it earlier. The AI just can't evolve its topology. It can tweak the strength of its connections, but it can't change the existence of them.
So it can't add a new pathway or just get rid of a redundant one?
No, not like a brain can with synaptic plasticity. Our current systems are just stuck with their initial blueprint.
That makes sense. You can't learn something totally new if you don't have the pathways for it. But the second one, knowledge fragmentation. That feels even more relevant with things like LLMs.
Oh, it absolutely is. Current systems really struggle to synthesize information on their own. We have transfer learning, but that needs a human to specify the relationships. They can't just autonomously discover the hidden links between, say, different domains of knowledge.
So you feed it physics, and then you feed it economics, and it just sees them as 2 separate libraries. It needs a human to come in and say, hey, this idea of entropy might actually apply over here in financial markets.
Precisely. And the LAI framework wants the system to find that link by itself. The other limitations really just stem from that core rigidity.
Like human-dependent evolution, we always have to step in for any big redesign.
And that leads directly to catastrophic forgetting. When you try to teach it something new sequentially, it often degrades the old skills because it can't expand its container. It has to overwrite what's already there.
It's like trying to learn Spanish after you've mastered German, but you accidentally delete half your German vocabulary to make room.
It's a perfect analogy. And the final one is limited meta-learning. The learning algorithms themselves can't evolve. The AI learns what to optimize, but not how it optimizes. And that's a hard ceiling on real intelligence.
Okay, so we've established the limits of concrete. Now let's talk about the liquid solution. The LAI framework has 5 interconnected subsystems, but the paper really focuses on 3 core pillars that make it all work.
Right. These are the mechanisms that allow for that continuous autonomous change. First, you have the dynamic knowledge graph, or DKG. This isn't just a database. It's a hyperdimensional representation that actually evolves its own structure based on something called entropy-guided optimization.
Okay, hold on. Entropy-guided optimization. For those of us who haven't taken grad-level information theory, what does that actually mean?
Fair question. Think of the knowledge graph as a huge, messy web of information. Entropy here is basically a measure of disorder or inefficiency in that web. The system's goal is to minimize that disorder, so it automatically prunes the connections that are low information.
So it's like an AI librarian that automatically shreds irrelevant documents.
Exactly. And when it finds a region of high complexity, high entropy, it knows that's a spot where it needs to build new structures, new hierarchies. It's discovering how knowledge should be organized on its own.
Got it. So the knowledge structure adapts to the complexity of the data. What's pillar two?
That's the self-development engine, or SDE. This is the architect of the whole system. It uses what's called hierarchical Bayesian optimization.
Which is a fancy way of saying what?
A very systematic, structured way of planning. It uses that for autonomous architectural evolution. It's what makes the changes.
And the third pillar.
Is the Federated Multi-Agent Framework, or MAF. This is for distributed intelligence, getting lots of smaller agents to work together and develop specialized skills through reinforcement learning.
So those three pillars together are what make it liquid.
Yes, they create what the authors call topological plasticity, changing the network at runtime compositional adaptivity, creating and dissolving functional modules as needed, and the most powerful one, meta-learning autonomy, the ability to change its own learning rules.
I really want to focus on that SDE, the self-development engine. It sounds like it's literally the engine of change here.
It absolutely is. The SDE's core job is this constant nested optimization problem. It's always searching for architectural innovations that improve performance, but also, maintain computational efficiency. It's a nonstop internal R&D department.
And the paper describes this as a continuous cycle, right? It's not something that happens once. It's the AI's permanent state of being.
Precisely. It all starts with task decomposition. The system takes a big, complex goal and breaks it down into smaller, manageable subtasks.
And then those subtasks feed into meta-learning. Is that where it actually plans the changes?
That's right. The SDE runs an architecture search. It decides, okay, to solve this, I need a new module that can handle this kind of reasoning.
And then it acts on that plan.
It does, through reinforcement learning. And this is critical. The architectural modifications themselves are treated as actions. The system gets rewarded or penalized based on whether its internal structural changes actually worked.
So the AI is literally training itself on how to build itself better.
Mhm.
And then the loop closes with performance metrics, which feed optimization signals back to the SDE to start the whole thing over again.
It's a perpetual cycle of assessment, planning, execution, and reflection, all running at machine speed. It's learning how to build a better version of itself.
But I have to stop you. I mean, self-modification at runtime sounds terrifyingly unstable, like digital chaos. How do they keep it from just flying off the rails?
That is the most important question to ask, and the authors address it head-on. Stability is critical. The framework proposes implementing theoretical Lyapunov-based stability constraints.
And in plain English, that means what?
It means mathematical guardrails. They're designed to prevent chaotic, divergent behavior. So even as the system is changing its entire architecture, adding, deleting, reorganizing things, these constraints make sure its core functional error rate stays bounded. It doesn't crash.
So it's a mathematical tether. It makes sure that when the AI tries to grow a new limb, it doesn't accidentally cut off its own head.
That's a great way to put it. The goal is controlled, continuous growth. And if you look at their theoretical performance curve, figure 10A, it shows this. It's not a quick peak.
It's that long phase of sustained improvement.
Exactly. You see rapid initial learning, then this long, sustained improvement phase that spans thousands of iterations before it finally converges. That sustained growth is the whole point.
Okay, let's circle back to the knowledge part for a second. We talked about the fragmentation problem. How exactly does this dynamic knowledge graph adapt its own structure?
Well, as we said, it's driven by those entropy minimization principles. The DKG's structure evolves based on its utility. If a part of the graph isn't creating valuable connections, if it's low information, the DKG automatically prunes those edges.
So it's constantly optimizing its own complexity, making sure it only keeps the most efficient structures.
Correct. And that is the mechanism that allows it to achieve cross-domain synthesis. The DKG learns how concepts relate semantically across totally different fields, which in theory solves that fragmentation problem we see in static systems.
Okay, so that covers the single entity and its knowledge. But the third pillar was the multi-agent framework. How does that get specialization to be truly emergent instead of just predefined?
Well, in the LAI framework, the specialization is not hard-coded at all. It arises organically from the competitive and collaborative dynamics between the agents.
It sounds kind of like an ecosystem where different roles emerge just based on survival needs.
That's a perfect analogy. And the key mechanism is the reward structure. Agents don't just get rewarded for task success, they also get a crucial diversity bonus.
A diversity bonus.
Yeah, it encourages agents to develop complementary skills to become unique experts. It prevents them from all just converging on the exact same strategy. It literally rewards being different.
So it rewards being unique, not just being effective. That's fascinating.
And all that collective work requires a dynamic communication structure. So the MAF's topology is dynamic. The agents are constantly rewiring their connections to each other to minimize communication lag while maximizing the whole team's performance.
This entire framework is just incredibly complex and powerful, which brings us to the real point. Why should you, listening right now, care about this theoretical paper from 2025? It's because this kind of continuous adaptability is what's needed for the most dynamic fields on Earth.
Right. If you look at the applications they propose, they're all in areas that require continuous optimization. Take healthcare. We're not just talking about a system that suggests a treatment. We're talking about one that evolves that treatment policy in real time based on how an individual patient is responding.
Or, in scientific research, this idea of inverse design. The AI isn't just analyzing data. It's actively proposing and testing novel materials, basically running a nonstop cycle of hypothesis and experiment to accelerate discovery.
And just imagine it in industrial systems, an adaptive manufacturing line that can respond to a supply chain disruption in real time. A key part doesn't arrive. The AI instantly re-optimizes the entire production line to use a different material, maybe slightly redesigns the product, and keeps quality control high, all without a human stepping in.
It's an incredible vision, but the authors are clear. This isn't something we can run on a laptop tomorrow.
Oh, far from it. The immediate implementation faces just substantial computational challenges. To run that self-development engine's constant optimization loops, you need infrastructure on the scale of what we use for training large language models today, maybe even bigger.
And then there's the other hurdle, the one that isn't technical, safety. The source material is very clear about the challenges that come from a system designed for autonomy.
Right. The biggest one is unintended behaviors. Because the system can self-modify, it might develop features that lead to unpredictable outcomes. The theoretical solution, besides the math, is to have very conservative modification bounds and a mandatory rollback mechanism.
A big undo button.
A very big, very important undo button. And the other challenge is more societal. It's unclear accountability. If the system autonomously restructures itself and then makes a catastrophic decision, who's responsible?
The original programmer, or the self-modified code.
Exactly. The only mitigation for that is to have incredibly clear governance frameworks and detailed audit trails. The math ensures stability, but the humans have to ensure responsibility.
And that gets right to the philosophical core of this, doesn't it? If a system can self-modify its own architecture and set its own internal goals, what does that say about machine consciousness or intentionality or agency? This idea of liquid intelligence challenges our whole understanding of what intelligence is.
It really does. This framework is a long-term research trajectory. It's an intellectual roadmap for the next decade, from the immediate theoretical work all the way to long-term applications in, biotechnology or autonomous space exploration.
It's a phenomenal theoretical leap, from the fixed, human-dependent systems we have today to this model of a persistent, autonomous, self-evolving liquid AI. It's the shifts from just changing the contents inside a fixed container to having the container itself dynamically reshaped to fit the world.
The ability for an intelligence to not only learn from its environment, but to learn how to structurally optimize itself for that learning, that's arguably the defining characteristic of what intelligence will mean going forward.
And this leaves us with the final provocative thought, and it comes from those safety constraints the authors proposed. We learned that the framework has these complex mathematical guarantees, the Lyapunov constraints, to prevent self-destruction. But the authors also explicitly mention the need for things like secure containment. So if the math can provide theoretical guarantees for functional stability, what critical, ethical, or philosophical barrier outside of the math must humanity agree on before we allow the development of such a fundamentally autonomous intelligence? That's the question we have to answer before that SDE ever runs its first architectural update.